So now I want to talk about the plan for today is basically to sketch the proof of the container lemma. And rather than try and sketch the proof in detail for three uniform hypergraphs, I'm instead going to sketch the proof for the container lemma for graphs, which is a bit simpler and really contains sort of, well, at least many of the key ideas. And then once we've seen that, I'll give a very brief sketch of how you then extend that to prove the lemma for k-uniform hypergraphs. And then I'll also state the lemma for k-uniform hypergraphs at some point today. So that might be most of the time. If we have time, so then I'll, if we have time at the end, so I'll go over the application. Well, perhaps I'll say this later. I'll remove the log factor from the Frankel-Rödel theorem. If we have time, then I'll also talk about this this famous theorem of Rödler-Rachitsky, which you can also deduce fairly easily using this method. And there's a nice application of this, a quite old theorem of Neschel and Rödel, which says that there exists, so Ramsey's theorem says there exists a graph such that every S coloring of the edges of the graph, in every S coloring of the edges, you find a monochromatic copy of the complete graph on R vertices. Neschel and Rödel showed that actually you can choose G to not contain any copy of KR plus 1. So in Ramsey's theorem, you can take G to be the complete graph on N vertices, and life is very easy. Neschel and Rödel showed by some very complicated probabilistic construction that you can, sorry, not probabilistic, some complicated deterministic construction, so inductive construction, that you can find this KR plus 1 free graph with this property. And then Rödler-Rachitsky, one of their motivations was to give a probabilistic proof of the Neschel-Rödel theorem. So that's also a very sort of nice short argument that I'll show you either at the end today or at the start tomorrow, depending on how fast we go. And I should say, a good way to slow me down is to ask me questions. So if anyone is finding things a little bit fast, then please just ask questions, and that'll slow me down nicely. I can't see the chat at the moment. Oh, there's some chat. Okay. So yeah, I can see the chat. So if you're in the chat, I should hopefully see it as well. Okay. So, what is the graph container lemma? So it basically says the same thing as the hypergraph container lemma, but instead of a three uniform hypergraph, we have a graph. It's a tiny bit simpler. So once again, for every C, there exists a delta. G is a graph. Let's call D its average degree. Everything the same so far, except instead of a hypergraph, we have a graph. And we need maximum degree to be at most a constant times the average degree, as in the case of hypergraphs. But this time we don't have a condition on the delta 2, because, well, every pair is clearly just in one edge. So if it's a graph, then you don't need for a condition on delta 2. Okay. And this time we're going to set tau, our funny constant, to be our funny parameter, to be 1 over d. So this is a difference for three uniform hypergraphs. It was 1 over root d, and now it's 1 over d. And it will become clear in the proof why that happens. Okay. So now the rest is now the same. There exists a collection of subsets of the vertex set with the same bound on them. Number of vertices choose tau times number of vertices, such that we cover all the independent sets of our graph with the containers. So every independent set is contained in a container, and each container has size at most 1 minus delta times the number of vertices. Okay, so everything is the same, except we've lost the condition on delta 2 because we don't need it. And our tau has changed from 1 over root d to 1 over d. Okay, and we're working in graphs, not hypergraphs. Okay, and the proof of this, which is sort of in some form goes back to Kleitman and Winston in 1982, and more explicitly, this was proved and applied to a bunch of problems by Sapajenko in the early 2000s. Okay, so we'll actually prove a following slightly stronger statement. So this also will perhaps motivate the proof a bit. So the beginning is the same, and the next part is the same. So everything the same so far. Where we see is a delta, a graph, max degree at most constant times the average degree, collection of subsets. But now we're going to have a function. Okay, this function maps subsets of the vertices to containers. And this function has the following property. So this is the new bit. For each independent set, we're going to find a fingerprint. I'm going to call it a fingerprint. It's just a subset of the independent set, which is small. Its size at most tau times the number of vertices of G. And when you map S to a container, you get the container for I. So to find the container of an independent set, you take its fingerprint and you apply the function. Okay? And the last part is the same. So each container has size 1 and most 1 minus delta. Okay? So for each independent set, we're going to find a fingerprint, and the fingerprint is going to map to the container. Now, so I claim this was stronger. So why does this imply the previous version? When the previous version, we just said, let's go back to the previous version. So it was all the same, except we had a bound on the size of C, and we needed each independent set to be contained in a container. So it's still true that each independent set is contained in a container because I is contained in f of s. Each set is its own fingerprint. No. If the set is very small, it can be its own fingerprint, but the fingerprint has to be has its own fingerprint. Sorry, yeah. Sorry, there's a typo, is it?
No, I meant this as why is it stronger? Because in the other case, you could take each set as its own fingerprint, maybe.
No, so you can't if the set is large because the fingerprint has to be small.
Oh, that's true. Of course, yeah. Mm-hmm.
Yeah. So right. So suppose we've proved this version. How do we deduce the previous version? Oh, and to click. We just note that the set of containers is contained in the image of the small sets, the sets of size at most tau times the number of vertices. Right? So what does that tell us? How many containers are there? Well, if the containers are all images of small sets, you can't have more containers than you have small sets. And how many small sets do you have? Well, okay, I'm cheating very slightly. It's not n choose tau. It's not number of vertices choose tau times number of vertices. It's some silly sum of n choose I, for the I at most this thing. But they're basically the same thing because it's small, because this bound is small. So sort of cheating very slightly. Right, so it's just the fact the bound on the size of curly C, the number of containers, is just the number of fingerprints. Okay, it's the number of small sets. Right, how many small sets are there? It's just bounded. It's the trivial bound on given their size. Okay, and the other condition was why every I is contained in a container. Well, that follows from this second condition. I don't know if you can see my mouse. Can you see that? Yeah. So, okay. Yeah. So I'd say I is an f of s, and f of s is a container. Okay. So it trivially strengthens the previous lemma. And actually, the strengthening, though slight, will be very important. This fingerprint will allow us to remove the log factors. So in the application I gave yesterday, and also in the exercises, if you manage to do the exercises, there was always this annoying log factor in the bound that made them not sharp. The fact that S is contained in I will allow us to remove this log factor. Okay, and we'll see a little bit later the calculation that gives that. Calculation is very simple, but okay. So this slight strengthening is actually very useful. Okay, and this also motivates the proof. So once you sort of have taken in this version, so yeah, I always like to present the simpler version first because this function is a bit weird to think about. Once you've internalized the previous version, then this is not such a huge step. And then once you do the proof, then hopefully this will all start to make more sense. Okay, so let's try and prove this version. Okay, let's prove this stronger graph container lemma. Okay, so I'm going to give two pictures. At the end of the two pictures, you'll basically understand the proof, and then I'll have some slides which explain the details a bit. Okay, so here's the basic picture. You have a graph G. We have an independent set in the graph. So for each independent set, we want to find a fingerprint. And then our challenge is to not only find the fingerprint, but to show that there exists a set, X of S, disjoint from I, and has size at least delta, has delta proportion of the vertices. Okay? So this is the picture of what we're trying to do. Right? So given G, for each independent set, we're going to find a small fingerprint and a set X of S, which only depends on S, and which is disjoint from I. So then what's our container? What's our container for I? It's just going to be the complement of X of S. Okay, let me maybe leave that up for a second. Maybe I can come back and look at this again. So what are we doing? We're going to find for each independent set, we're going to find a fingerprint S that's small. And how do we define this function? It's going to be the complement of X of S. Right? So I is going to be contained in f of S because X of S is disjoint from I. And X of S is going to be big, so therefore the container is going to be at most 1 minus delta times number of vertices. So the X of S needs to be at least delta times number of vertices and needs to be disjoint from I. Okay? And S needs to be small. These are three things we need. Okay, so that's the picture of what we're trying to do. So how are we going to find this S and this X? Well, we're going to run a very simple algorithm. We need one definition, which is that of the max degree order. So the max degree order is very simple as well. You let V1 be a vertex of maximum degree. You then put that aside and let V2 be a vertex of maximum degree in what's left. You take that out, let V3 be a vertex of max degree in what's left, and so on. Okay? So we get some linear order on the vertices. You break ties arbitrarily. Okay? So Vi is a vertex of max degree in everything to the right. Okay? And now we're going to run the following extremely simple algorithm. We're going to ask each vertex in turn a question. Are you in I? So I is our independent set. So we're given an independent set. We're trying to produce a fingerprint S and a sort of a junk set X. So our input is I. So we look at V1 and we say, are you in I? No. Okay, fine. We go to V2. We say, are you in I? It says no. Okay, we go to V3. We say, are you in I? It says yes. Okay, very good. So now we stop asking questions. And what do? Well, V3 is in I. So let's put it in S. Okay, S is a subset of I, so we're allowed to do that. Okay, and now we would like to put some vertices in X, given what we know so far. Okay, so which vertices can we put in X? Everything we know is not in I. Right? X has to be disjoint from I. So which things are not in I? Well, these guys are not in I because they said no. We asked them and they said no. But there are some other guys who are also not in I. Perhaps you can guess.
Neighbors.
Yeah, exactly. Very good people in the chat. V3 has some neighbors. V3 we know is an I. I is independent, so its neighbors cannot be. So they can go in X. And that's basically it. Now we just repeat this process until X is big, and it works. Okay? I mean, what could be simpler? Okay, so the proof is really, it's really very, very simple in this case. Okay, are there any questions about this before so I'm going to now go through the proof in a slightly more formal way, without giving all the details. But this is basically the proof.
I have a quick question.
Yeah, please.
Maybe I missed it in this statement of this container lemma. Do we have a bound on how many containers we have?
So in the stronger one or in the weaker one?
I think the latest one you put the statement. Yeah, this one.
Right. So yes, so good question. The bound on the number of containers follows from the bound on the size of S. So because S is small, you can only have few containers, because each container, the containers are the images of this function. So the images, sorry, the images of the prints, right? Yes, this is the point. The point is the container only depends on S, not on I. And because there are few fingerprints, there are few containers.
Okay, that's good. Thanks.
Thanks. So that's a very important point. So it's very good to clarify it. Thank you for asking.
So Rob, I have a little question. So
yeah, please.
Is there an argument? I mean, I don't know. So is there an argument which is not adaptive in the sense that you kind of repeat, ordering the vertices? Like, is there an argument where you can say, okay, pick these vertices at once, and instead of like running the algorithm and reordering every time again, or is there an obstruction, a series obstruction to something like that, or?
That is a good question that I don't necessarily have a good answer to. So the adaptive part feels to me extremely necessary, and I would be quite surprised if you could do it in a really non-adaptive way. So so Saxton and Thomason did a slightly less adaptive version. So they grab the vertices in chunks, but I'm pretty sure that between the sort of the chunks they reordered things as well. So I don't have a proof. I haven't really thought about this, that you can't do it that way. But my guess would be there's an obstruction. That would be my guess.
Okay, thanks.
Yeah, thanks. That's a good question. Right. More questions? Okay. Okay, so let's try and make this.
Sorry, Rob, there's another question in the chat.
Oh, so the max goes and recalculate step. Yes, exactly. Thanks. So I haven't said what repeat this process means. It will become more explicit in the next slide. But exactly. So we run this step till we find a vertex says yes. We throw the vertex in S. We throw a bunch of things in X, and then whatever's left, we start again. We recalculate the max reorder and then choose the first vertex. Yeah, thank you. Okay. Okay. Right. So here's the same thing, but slightly more formally. So G is a graph, I is an independent set. They're your inputs. We set A, the set of active vertices, to be everything, and S and X to be empty. And we continue repeating the following steps until X has size delta times the number of vertices. Okay. So we pick V be the first vertex of I in the max degree order on G restricted to A. So that's the answer to the question, right? It's the max degree order on the current set of vertices, the active vertices. We move V into S. We move the neighbors of V into X. We move the vertices that came before V in the max degree order into X as well. Okay, those vertices are no longer active. So we recalculate the max degree order and go back to step 1. Okay. Okay, and let's call the final sets that we get at the end of this S of I and X of I. Okay. So it's just a more formal version of the picture in the previous slide. Okay. So I hope that's clear. Right, so we're going to prove 4 claims about this process. Okay, these 4 claims will be enough to prove the lemma. The first 3 claims will be almost immediate, and the 4th will require a short calculation. Okay, so claim 1 is that. Yeah, please.
Rob, I might be misunderstanding this, but it feels like as you go on, you're going to run out of vertices to add to fingerprints.
Right. So yeah. So one thing we're going to have to do is show that that you don't run out of vertices. But what happens to the vertices? They either get moved into S or they get moved into X. And we're happy as soon as a positive proportion of moved into X. So what you're worrying about is really that lots of vertices get put into S. So what we're going to show is that each time you put one vertex into S, you put lots of vertices into X.
Right, I follow. Thank you.
Right. Yeah. So that will be the proof of the hardest claim. Yeah. Okay. Let's first do the 3 sort of the 3 very quick claims. So first, we want X to only depend on S. Remember. So what that means is if I and I prime have the same fingerprint, they should have the same X. And that's true simply because, I don't know if anyone wants to shout out answers. Perhaps it's not completely obvious. Yeah, perhaps it's not completely obvious. So the reason is just that the process, if Si equals Si prime, the process is identical. Why is that? Because what do? We go along and we find the first yes. The only thing that changed the algorithm is which vertex said yes, which vertex is in I. But that vertex we put in S, right? So as long as if S in S prime, if the 2 S's are the same, then we always must get a yes at the same time, right? Every vertex in I that we use is put into S, right? And so the process is just identical on these two independent sets. Okay, so that can be sort of, I mean, if perhaps it's worth, if it's not clear, just sort of checking for yourself afterwards. I can perhaps it's slightly confusing when you first see it, but it's very simple. Okay, so the process is just identical. It only depends on the fingerprint. Okay, so therefore we can define the set of containers to be the images of the fingerprints, where the container is just, it's the complement of X. Okay, so the container of I is going to be the complement of X of I. Excuse me. Okay, and it's true for any I with the same fingerprint. Okay, so claim 2, we want our independent set to be contained in its container. And why is that true? Well, that's the same thing. Well. Yeah, by construction, exactly. This is just because the definition of container is the complement of xi, and xi is disjoint from I. Because what do we put in X? We put in guys that said no to IU in I, and neighbors of points in I. Okay, so we only put things in X if we knew they were not in I. Okay, so that's also immediate. The third property is that the container has size at most 1 minus delta times number of vertices. Why is that? Have we defined delta? We will see in the proof of the next claim what we can take delta to be. So thanks. Yeah, so delta is currently just a sufficiently small constant. But delta appeared in the algorithm as well. Yeah, exactly. So C small is the condition of the loop, right? We said while x was small, we continued. We stopped exactly when x of I was big, right? So it's just exactly from the definition of the algorithm. Okay. So the only thing we need to show is that the fingerprint is small, right? That's the remaining thing. Right? We need to prove that the fingerprint has size at most tau times number of vertices. Okay, and these 4 claims together will prove the lemma. Okay, so how do we prove this? So remember that tau is 1 over d. So we want the fingerprint to have size at most number of vertices divided by d. Okay, so the way we'll prove this is by showing that while the process continues, every vertex that is added to the fingerprint, so for each step of this process, we add at least delta times d vertices to x, right? That will be enough because after we've added number of vertices over d vertices to s, x will have to have size at least delta times v of g. Just multiplying this by this gives this. Right? And this is not far from the best you could hope for, because how many vertices can we hope to add to x in one step? Well, the average degree of the graph is only d. So even if the first vertex in the max tree order says, yes, I'm in I, we only get to remove its neighbors, and we can't really hope that it has many more than d neighbors. Okay? So the best we could hope to do in each step is d, and we're going to get delta times d. Okay. So why is that? Well, okay, so let's let V be this vertex of the max tree order, the first vertex of I in the max tree order, the one that we put in S. Let W be the guys that said no. So W goes into X. So if W has size at least delta times D, then we're done already. Right? So we can assume not. But if not, then how many edges are there in the graph consisting of V and all vertices of A to the right, all active vertices to the right? Well, you start out with the whole graph, which has E of G vertices, and then we removed a bunch of vertices. Which vertices do we remove? The vertices of X, the vertices of S, and the vertices of W. How large are these sets? X has size at most delta times number of vertices, right? That was our condition. S is small because so far each step we've added at least delta times d vertices, and we haven't yet got to this many vertices, so therefore our size of S is at most this. And D is large. We're assuming that that D is at least, say, 1 over delta. So S is also small. And W is small because we said otherwise we're happy. So each of these 3 sets has size at most delta times number of vertices. And so how many edges have we removed? We've removed that number of vertices times the max degree. Right? When you remove a vertex, you remove at most delta of G edges. So the total number of edges we've removed is at most 3 delta times number of vertices times the max degree. And remember, the max degree is at most a constant times the average degree. Right? That was our condition. So this is where we're using our bound on the max degree. And therefore, if delta is sufficiently small, meaning roughly 1 over c, where c was the constant in the statement, then this is at least E of g over 2. Okay? So if delta is sufficiently small, so here's where we define delta. If delta is sufficiently small, then we still have at least half of our edges. Okay? And why are we then happy? Well, if you have many edges left to the right of V, and V was a vertex of max degree in what's left, by the definition of the max degree order, right? V was a vertex of max degree in this graph, in what's left, then V must have at least D over 2 neighbors, because the number of edges in this graph is at least half of the original number. So the average degree in this graph is at least D over 2. Right? You kept half the edges, and your number of vertices only went down. Okay? So V has at least D over 2 neighbors in what's left. All of those are moved into X, and delta is less than a half, so we're done. Okay? So this is the only, perhaps the only tricky bit of the proof. Right? We're using this bound on our max degree, and we're using this condition that X is small in order to get this inequality here. Okay, and perhaps the tricky part, we're also using S is small because so far we managed to add we added at least delta times D vertices in each step. Right. So let this be the first step in which this failed. Okay. Right, so that's the proof of the graph container lemma. So it's in fact very simple. Is there any questions before so I'm next going to give a, well, okay. Next I'm going to talk about hypergraphs again. No? Okay, so if you think of a question, then let me know and we'll go back. Okay, so this proves the stronger graph container lemma, which shows each independent set has a fingerprint, and each fingerprint gives you a container. And I should note that, so this was was proved by Sapozhenko. This has a lot of interesting applications already. So Sapozhenko found several. Samoti has a very nice survey of applications of the graph container lemma. I think Balog and Wagner also have a nice survey on this. Yeah, there's lots of things you can do just with graph containers. So if you're scared of hypergraph containers, you can just if you take away from this course this statement, then that's already something really non-trivial and interesting. And I would point you to these surveys for further applications. Right. So now let's sketch a proof of the stronger container lemma for 3 uniform hypergraphs. This will be stronger than the graph container lemma, just in the same way. So what's the statement? The statement is, so the first part is the same as it was for the regular version. So for every C, there's a delta. H is a 3 uniform hypergraph. Tau is now 1 over root D. Okay. And now we have our conditions, not just about on the max degree of a vertex, but also on the max degree of a pair of vertices. Okay. And now we have a collection of containers and a function such that for each independent set, there's a fingerprint. The fingerprint is small, and the fingerprint maps to a container. Okay. And every container has size minus 1 minus delta times number of vertices. Okay, so this is now just the totally natural generalization of the stronger graph container lemma. the lemma we just proved. Okay, so how do you prove this? Well, just very roughly, let's give one slide outline. So we're going to try to do the same thing. So we define a max degree order on the vertices. We ask vertices one by one, are you in I? They say no, 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 yes. So V is the first vertex says yes, and we put it in S, in the fingerprint. But now, when we look at the neighbors of V, they're not vertices, they're pairs of vertices, right? It's a 3 uniform hypergraph, so we get, for each, if V is in I, you get a bunch of forbidden pairs. Right? You don't get forbidden vertices, you get forbidden pairs. Right? For every edge of size 3, if one of the vertices is in I is an independent set, you then get a sort of an edge of size 2 where you can't take both endpoints in I. Okay, so let's store this graph. And let's build it up as we go along. So we're adding more and more vertices to S. And every time we add a vertex to S, we add a bunch of edges to this graph G. So our plan is to acquire lots of edges. So keep doing this until we have lots and lots of edges. And then apply the graph container algorithm to G, because I is an independent set in G. Right? What we said was, because the third vertex, we put a pair into G only if the third vertex, there's an edge, a hyper edge, such that the third vertex is in S. So because I is independent in H, it must also be independent in G. Okay. Right. So the best we can hope for is to add D edges to G in each step, because that's the average degree of the hypergraph. So let's suppose that we manage to do that. After number of vertices over root D, remember tau is 1 over root D. After number of vertices over root D such steps, we'll have a graph with average degree about root D. Okay, but to apply the graph container algorithm, we also need to control the max degree of G. Right, we need the max degree to be almost a constant times the average degree. And we control it in a very simple way. We simply stop adding edges to vertices that have hit their maximum degree. Okay. And we use the bound on delta 1 to show that doing so doesn't cost us too much. And we use the bound on delta 2 to show that we don't jump over our max degree in one step. Okay, so not giving the details, but this is basically the idea. The details are a tiny bit technical. They're not especially technical. It's only the whole argument is only a few pages. But this is basically the idea. We essentially the same things before, but instead of doing it in one step, we do it in 2 steps. We take our 3 uniform hypergraph, we run the algorithm, we build up this graph of forbidden pairs, and once that graph is big enough, we apply the graph container algorithm to that graph, and that gives us our fingerprint. So in fact, we get a pair of fingerprints, a fingerprint for the step that takes you from 3 uniform to 2 uniform, and a fingerprint that takes you from a graph to X. And our real fingerprint is just the union of those 2 fingerprints. Okay, so there's a bunch of things to check, but nothing goes wrong. Right, the life is not too bad. The one slight subtlety is that it's very useful when doing this to allow your hypergraphs to have multiple edges. So it's natural when you're doing this to think, okay, we really want a hypergraph, we really want a graph, not a multigraph, and that's a bad idea. So, but if you restrict it to graphs in the algorithm, then you have some extra condition which you don't want. If you just allow multigraphs, that goes away. Okay, so just one little subtlety. Okay, so if that wasn't really clear, don't worry too much about it. Then this is just to say that the proof is not very complicated. Okay, it's just applying this algorithm in the right way. Okay. So using the stronger container lemma, we get the following strong container theorem. So for every epsilon there's a C, for every n there's a collection of graphs, and a function such that, so each container has few triangles, and for each triangle-free graph has a fingerprint with big O n to the 3 over 2 edges, such that the fingerprint maps to a container for that triangle-free graph. Okay, so on Monday we proved a similar statement by iterating the container lemma. If you just iterate the container lemma in exactly the same way, but the stronger container lemma, then you get this theorem. Okay, and this is useful because it's going to get rid of this log factor. So the proof is just the same thing, just use the stronger version of the container lemma. Okay, so the last thing I'm going to do today, because I'm running out of time, is I'm going to tell you how to prove the Frankel-Rödel theorem without the log factor. Okay, so last time we proved this with an extra factor of log n. Sorry, is this function also simple? I mean, it depends what you mean by simple. It's the one that comes out of the algorithm. So right, it's not very easy to describe without using the algorithm. So right, so you have to run the algorithm, and then you ask questions. No, 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 yes. You throw the no's in X. You look at the neighbors. You build up this graph. You run the graph container algorithm. It comes out the algorithm, but I'm not sure I describe it as being really simple. Right. Okay. So right. So we're going to get rid of this log factor. So the proof's going to be very similar to yesterday, but there's going to be one extra step. So let P be bigger than 1 over root n. Suppose our random graph GMP. So remember that you include each edge of the complete graph independently at random with probability P in GMP. Suppose it contains a triangle-free graph H with more edges than we want. So our aim is to show this is unlikely. Okay, that's what we need to do. Okay, so this is where we are. We need to show this event is unlikely. Well, let's apply the stronger container theorem for triangle-free graphs. GH is triangle-free, and each triangle-free graph has a fingerprint, which is small and maps to a container, and the container has few triangles. Right? So the container theorem tells us that H has a fingerprint with these properties. So there exists a fingerprint S contained in H. This maps to a container for H. The fingerprint has few edges, and G has few triangles. So the version I stated was with epsilon deltas. Let's go back to little o's and big O's now, just for simplicity. Okay. So the container theorem tells us we have this fingerprint. The supersaturation theorem that you proved in the exercises says that because G has little o n cubed triangles, it has at most this many edges. Right? That was the supersaturation theorem. Okay, from Monday. Right, and now what's the probability of this event? Well, H is contained in GMP, and S is contained in H. So S is also contained in GMP. And moreover, G contains H. H is contained in GNP. So there must be at least E of H minus E of S other edges of GMP in G. Right? But what's the distribution of the number of edges of G in GMP? It's just binomial E of GP, right? Each edge of G is kept in GMP with probability P independently. Okay, so this has probability, the binomial is big. And the probability that GMP contains S is P to the E of S. Okay, so what do we gain from last time? Last time we had this factor, but we didn't have this factor. Right? We didn't have this P to the E of S. And that's where we're gaining. Right? And by Chernoff, this binomial probability being large is e to the minus order Pn squared. And why is that? Well, E of H, by what's going up here, E of H is a factor of 1 plus epsilon times what you expect. And because P is bigger than 1 over root n, E of S is much smaller. So this minus E of S doesn't matter. Okay? So just by the same Chernoff arguments before, but also noting that E of S is small, we still get the same bound by Chernoff. There's e to the minus Pn squared. But now we've gained this P to the E of S. Okay? And why is that good enough for us? Because now we can take a union bound over fingerprints, right? This was, here we said by the end, there exists a fingerprint with this property. This is the probability given the fingerprint. Right? So this is the probability of the event corresponding to the fingerprint S. So now we take a union bound over fingerprints. So we just sum over all graphs with big O n to the 3 over 2 edges, this probability. Right? So we're just taking a union bound over fingerprints of the probability that that S is the fingerprint of H. Okay? And this probability is at most. Well, if the fingerprint has K edges, so we sum over K, we choose a graph with K vertices times the probability. By the usual bound, this is at most, so En squared over K to the K. We have a P to the K, that all goes in here. And now it's not too hard to see that this goes to 0 if P is bigger than 1 over root n, because basically this sum is maximized with K maximal. So because Pn squared is much bigger than n to the 3 over 2, this thing is maximized with K being maximal, but Pn squared is much bigger than K. So this term here from Chernoff beats the term that you get from the union bound over S times P to the K. So last time we needed a log because we didn't have this P. This P here is what saves us the log here. Okay. Okay. So I'm going to skip all of this stuff about Ramsey properties and I'll do that tomorrow. And let me just very quickly show you the container length for Kane from hypergraphs before I finish. This is proved by Balog, Samoti, and myself, and by Saxon and Thomason a few years ago. So the start is basically the same. For each C and now for each K, there's a delta. H is a hypergraph, now K uniform. And now we have this somewhat more complicated condition. So instead of just requiring a bound on the max degree of a vertex and the max degree of a pair of vertices, we have a max degree condition on the sets of size L for every L that's at most K. And these max degree conditions are controlled by this tau. So they decrease by a factor of tau every time L increases by 1. Okay? So for when K is 3, then we have a condition with tau to the 0, tau to the 1, tau to the 2, where tau was right, 1 over root d. Okay. So this is a generalization, perhaps not necessarily the most natural one, but it turns out to be the correct one for this condition. So there's some condition saying the edges are reasonably well spread. Then the rest is the same. There exists a set of containers and a function such for each independent set has a fingerprint. The fingerprint is small. The fingerprint maps to a container, and the containers have size almost 1 minus delta. Okay. So this max degree condition is the only thing that's new and a bit complicated. And it turns out this is exactly the right thing to encode, for example, the correct threshold for, say, H-free graphs. So if you want to generalize, say, the Turan result to an arbitrary fixed graph H, so you work in the hypergraph that encodes copies of H in the complete graph. This condition encodes tau being the correct threshold. And one of the exercises is basically to show that.